Okay, yeah, so I've been working on this alongside with Dave Glenar, Tim Stubbs, and Ludmila Kolokolova. So, why is this research important? The double asteroid redirection, or DART mission, is designed to impact the moon dimorphos of the Didymos binary and demonstrate the kinetic impactor technique. Observations from the ride-along companion Lysia cube of the spatial structure and temporal evolution of the resulting ejector plume will help determine the vector momentum transfer and constrain physical properties such as strength and porosity. Optical scattering properties of the ejector particles used in radiative transfer plume simulations will dictate the relation between observed brightness and inferred ejector mass. So you need a realistic scattering model for plume particles to ensure accurate interpretations. Next, please. So a vital part of the radiative transfer model then is the scattering model, but what we don't know is how does the choice of scattering properties affect the model brightness results. To that end, we created an experiment, a series of scattering models for impact plume ejector fragments based on plausible analogues, including laboratory measured millimeter grains based on comparison with Bennu particle photometry. Additionally, we included a scattering model for the EZA, but more in realistic isotropic scattering approach. We used these scattering models in a radiative transfer plume simulation of scattered sunlight for optical depths ranging from 0.1 to 10, including multiple scattering effects with the DISort software. Our focus is the plume scattering properties. We make no assumptions about time evolution of velocity or even the fragment mass distribution. That is for other folks, such as Farnstock et al. So the results are basically from simulation. The results from the simulations indicate are often dimmer than the simpler but less realistic isotropic scatterers. So this allows us to answer the question of how important are realistic scattering properties to mass estimates. The answer seems to be very, as wrong values will lead to errors in inferred ejector mass and momentum. So let's explore that in a little bit more detail. So for our model, next slide please, we use the full encounter geometry of Cheng et al. 2020, but here we show a simplified view of the evolving viewing geometry, showing how the Lysia cube line of sight varies with time. The spacecraft is moving from right to left. Step 1 shows the separation of Lysia cube from DART before impact. After impact, we model the scattered sunlight using the colored lines of sight in steps 2 to 4, seeing the plume from in front in step 2, from the side in step 3, and from behind in step 4. To build our millimeter grain models, we used laboratory measured phase curves for 2 large grains or several millimeter dust analogues taken from Munoz et al. 2017 and 2020, selected from a range of larger samples shown in the plot on the right here. For our plume simulations, the phase angle, alpha, the inverse of the scattering angle, corresponds to the figure on the left. Our chosen models, the Etna volcanic particles and luminosilicates, are shown in blue and green respectively. But how did we choose them? We started by calculating the phase coefficient, the negative slope of the brightness in magnitudes, so dm by d alpha, shown in the left-hand figure here. The chosen models can be considered limited cases for the scattering behavior of the DART impact fragments. The dark volcanic Etna sample exhibits moderate porosity and a rough surface. Next one, please. Between alpha equals 80 and 110 degrees, the phase coefficient is small, within range of values for naturally ejected Bennu particles with the best fit density of about 1,340 kilograms per meter cubed. After a 25% downward correction to account for the high albedo as well for Didymos and dimorphos, which is basically shown by those orange boxes there. So the Bennu constraints shown before and after the albedo adjustments are those orange boxes, where you can see that because dimorphos is brighter, we have to shift the box down. So the aluminosilicate is looks at the other extreme, and this is more compact, exhibiting a phase coefficient more closely resembling a dysfunction of larger objects from alpha is about 90 degrees up to the inflection point near 140 degrees. Now, neither of our measured phase curves actually go all the way from 0 to 180 degrees, so some extrapolation is required. So extrapolation to 0 degrees is done by linear fitting to dm by d alpha, and going up the other way to 180 degrees is done by matching the high phase measurements to a scaled Henry-Greenstein phase shape. So we use our millimeter grain curves along with some others to investigate the model brightness versus optical depth relation. So these are the phase curves that we're using. So the millimeter grain curves are colored as before. Those small grains are unlikely to represent a potential fine grain portion, grains with a radius less than a millimeter. We've included the phase function shape for large Libyan sand grains, the orange curve taken from Munez et al. 2007, and extrapolated using the same method that we used for the millimeter grain curves. The pink line, labeled DART here, shows the phase curve adopted by Farnstock et al. in their upcoming paper on the DART impact ejector simulations, and it uses a...
Yeah, be right there.
Sorry? It uses a constant phase coefficient constrained by Bennu photometry. The final case is the simple but unrealistic isotropic scatterers model in white. We now... Okay. All right, we now had lines showing the location and the phase function for the viewing geometry line of sights included in our simulation, so the figure I showed you before, shown in where t is the time after impact, where step 2 is viewing the, from the plume from in the front, step 3 from the side, and 4 from behind. Though diffraction is being included in our phase curve models, as shown by the solid lines, it can be seen that its emission, the dashed lines, has no effect on our chosen viewing geometries. So now we can show the results. So we start with step 2, it equals 100 seconds after impact, where LSE is observing the plume from the front, as shown in the diagram. The small plot in the bottom shows the phase curves and where the current viewing geometry is at alpha equals 34.7 degrees. We model the beams IA in red and IB and blue on the figure from plume surfaces A and B. So these are the results plots. In magnitudes per square arc second, so a logarithmic scale versus the geometric optical depth down along the bottom. To estimate brightness of the plume surfaces are modeled as a homogeneous layer of scattering fragments that follow a power law, the same power law size distribution as used in Cheng et al. 2020. So as you can see, all brightness predictions, apart from isotropic, are similar within a factor of 2 of each other. Some divergence can be seen at higher optical depths, particularly from plume surface B. And you can also see that the brightness values from the Libyan sand case, the orange curve, basically start to get brighter, and that's basically because they're measured as small grain cases, and small grains tend to be brighter. So moving on to step 3, at t equals 165 seconds at a phase angle of 52.5 degrees, and here LSE is viewing the plume from the side. And what you see is basically the radiance IB prime, which is a combination of IB and IA attenuated by transmission through plume surface B, as shown by the equation on the right. Results are similar to the previous time step, though an increase in divergence between the curves is seen at lower optical depths when compared with the previous results. Again, isotropic scatterers are the outlier. Finally, we have step 4, it equals... Thanks.
We have about 2 minutes.
Thank you. After impact, with a phase angle of 102.7 degrees, where LSE is observing the plume from behind. Significant divergence between the models can now be seen. This would lead to significant difference in inferred ejector mass estimates when relating mass to optical depth with an assumed size distribution. It turns out, thank you, that another important parameter controlling plume brightness is the assumed minimum grain size, Amin, for the size distribution. Results shown here are for a representative sample using the millimeter grain models, but you see something similar across all the models. A factor of 4 variability is seen when varying Amin between 100 microns and 1 millimeter. Next, please. So what have we learned? With the exception of isotropic scatterers, all brightness predictions are similar, within a factor of about 2, at small phase angles, so their tau, optical depth, can be linked to plume areal mass. However, results diverge dramatically at larger phase angles. In other words, inferred ejector mass estimates here would also diverge, and results are sensitive to the assumed minimum grain size of the distribution. Therefore, adopting a realistic scattering properties model for ejector particles is critical for accurately interpreting and understanding observations of the DART impact. Next, please. Thank you. So, to that end, we've got work in process as well. This is much work in progress, and we're just doing more stuff. So, further numerical testing with DSORT, testing the impact of size distribution choice, fragment shapes, etc., the usefulness of RGB imaging and color, and finally using our model to create a simulated LSE imaging sequence of the evolving ejector plume. And with that, I'd like to thank you very much for listening.